Hello, and welcome to our discussion of solving a transport equation with a product onsets, also called separation of variables for partial differential equations. We want to solve the transport equation ux minus 4ut equals 0 for a function u that depends on the variables x and t by making the product onsets, or assuming that u has the form, u of xt is equal to big X of x times big T of t for two functions big X and big T of one real variable each. Now we already know the general solution because we've watched the video on the transport equation and we've read the notes on it. We know that u has to have the form u of xt equals f of minus 4x minus t for a function f that is differentiable on R. So let's put in the special onsets u of xt equals big X of x times big T of t, and let's figure out what big X and big T have to be, or what they have to do. The natural thing to do is to plug this onsets into the differential equation and start differentiating. We need the first derivative of u with respect to x, that's partial x on big X of x times big T of t. The big T doesn't depend on x, so we pull that out to be big T of t times x derivative on big X of x. So that's big T of t times big X prime of x. And likewise, first partial of u with respect to t is partial with respect to t on big X of x, big T of t. Big X doesn't depend on t, that's why it's an x. So we factor that out. We have big X of x times t partial on big T. That's big X of x times t prime of t. And those are the only derivatives we need for our problem. So we plug them in. We want 0 to be equal to ux minus 4ut. That's big X prime of x times big T of t minus 4 big X of x times big T prime of t. So this is what big X and big T have to do. They have to make this equation equal to 0. If we know that big X equals 0 or big T equals 0, then since we have a product, u equals big X times big T, this forces u equal to 0. And that certainly is one solution to the transport equation, which is, after all, a linear homogeneous PDE. It's also not a very interesting solution. So we won't pursue that further. We'll assume that big X and big T are not 0. And we know that when things are not 0, we can divide by them. Let's rearrange our problem. 0 equals big X prime of x times big T of t minus 4 big X of x times big T prime of t. Just by adding one thing to the other side, we get big X prime of x times big T of t equals 4 big X of x times big T prime of t. And because we're assuming x and t are non-zero, we can divide. This means that big X prime of x divided by big X of x equals 4 big T prime of t divided by big T of t. Now look carefully at this last equality. We're assuming this has to hold for every x and every t out there. So let's take t equals 0. What does this mean? We need, for any x, big X prime of x divided by big X of x to be equal to 4 times big T prime of 0 divided by big T of 0. Let's call 4 times big T prime of 0 divided by big T of 0 lambda. We don't know what lambda is, but we know it has to be some number. So this means that x by itself has to satisfy big X prime of x divided by big X of x equals lambda. This rearranges into something familiar. Big X prime of x equals lambda times big X of x, and that is just a first-order differential equation for big X. And we know how to solve that without even thinking about it. We have big X of x is c times e to the lambda x, where now c is another constant. So we've solved for big X. What about big T? Well, we had this relation big X prime of x divided by big X of x equals 4 times big T prime of t over big T of t. And that holds for all x and t. And we know that big X prime of x divided by big X of x is equal to some number lambda for all x. So we have to have 4 times big T prime of t over big T of t equal to lambda. This rearranges to a familiar ODE. Big T prime of t equals lambda divided by 4 times big T of t. So of course, big T of t is now equal to a constant c tilde times e to the lambda t over 4, where c tilde is another constant that doesn't have to be the same as c from before. So with our product ansatz, u of xt equals big X of x times big T of t, we get u of xt is c times e to the lambda x times c tilde e to the lambda t over 4. And let's just group our constants together, so that's c times c tilde, and let's put our exponentials together. This is e to the lambda times the quantity x plus t over 4. And let's make this a little nicer. First, we'll absorb the product big C times big C tilde into one constant c equal to big C times big C tilde. So if c is any real number and c tilde is any real number, then their product can be any real number. So we don't gain anything by having two constants c and c tilde out in front of u. Now we should think back to what we know already. We remember what the general solution to the transport equation ux minus 4ut equals 0 was. So we should ask ourselves, can we write c e to the lambda x plus t over 4 equal to f of minus 4x minus t for a particular function f that depends on some real variable, capital X? And the answer is yes. If we do a little arithmetic, we can factor lambda times the quantity x plus t over 4 is minus lambda over 4 times minus 4x minus t. So c times e to the lambda x plus t over 4 is really c times e to the minus lambda over 4 times minus 4x minus t. So if we define f of capital X to be c e to the minus lambda over 4 times x, then we get u of xt equals f of minus 4x minus t for this very particular f, which is exactly what we expected from the transport equation. So what we've done here, we made the product ansatz, we figured out what the factors in the product ansatz had to be, we put the factors back together, we simplified our answer a little, and we checked against what we already know and found that yes, this agrees with the general solution to the transport equation if we take our function f to be something special. So again, we know that our solution is u of xt equals f of minus 4x minus t, where we've defined f of capital X to be c e to the minus lambda over 4 times x. And we have two free parameters in this solution, c and lambda. This is not surprising. Our transport equation had two derivatives, ux and ut, so every time we get a derivative, we expect to have a free parameter, sort of like what we saw with initial value problems in differential equations. However, we need to be careful here. We do not get as general a solution to the transport equation using separation of variables as we did with our prior and original approach to solving the problem. Here's why. If I were to define u of xt equal to sine of minus 4x minus t, this would also be a solution to ux minus 4ut equals 0, based on what we got in the general solution to the transport equation. But you cannot write sine of capital X equals c e to the minus lambda over 4 times capital X no matter how you choose the constants c and lambda. So here is the moral. Separation of variables need not give us the most general solution. If separation of variables works, it will give us a solution, but we could be missing out on something that a different analysis would tell us about.